Assalamu alaikum warahmatullahi wabarakatuh. My name is Saleh Ali, and today I will talk about the first chapter of automatic control, and it will be the introduction. This presentation will be under supervision of Dr. Trian Ahmaduddin. All the information of this presentation will be taken from the textbook of Control Systems Engineering by Norman S. Nice. Here, as we can see, these are the titles included in this chapter, and we will go through them, inshallah, during this presentation. After finishing from this chapter, we will be able to understand several things. First of all, define a control system and describe some applications. Describe historical developments leading to modern-day control theory. Describe the basic features and configuration of control systems. Describe control system analysis and design objectives. Describe control system design process. Describe the benefits from studying control systems. Control systems are fundamental to our modern world, impacting numerous aspects of our lives, from the launch of the rocket to the precise operation of manufactured equipment, and even the intricate working of human body. Control systems are constantly at play. These systems designed to regulate and direct processes are not limited to technology. They are also evident in natural phenomena and can be applied to the model abstract concepts, such as the relationship between students' study time and their academic performance. And to define the control system, we should know what's the system and what's the control. For the system, it's composed of a set of intricate components affected by an external input to produce an external output. Secondly is the control, which is a hidden technology that you meet everywhere in many applications. Its objectives are to stabilize the system and to maintain the desired performance. So after we understand the two terms, now we can define the control system, which is an interconnected arrangement of subsystems or processes or plans that designed to achieve a specific output with desired performance in response to given input. As we can see in the figure, the simplified description of control system, and there are a lot of examples like elevator thermostats and automated manufacturing. And now we will talk about the advantages of the control systems. Firstly, the power amplification. Control system enable the operation of high power devices with low power inputs. For example, a small knob can control the rotation for a large powerful radar antenna. Secondly, remote control enables the operation of system is inaccessible or hazardous environments. For example, including robot arm using in radioactive zones or for deep sea exploration. Thirdly, convenience of input form. That means allows for user-friendly input method while producing complex output. For example, a simple thermostat setting controls a complex heating system. Lastly, compensation for disturbance. That means enable system to maintain desired performance despite external and internal disruption. For example, an antenna control system that can counteract wind forces and maintain its position. And here in the figure, as we can see, it's an example for a remote control with a robot. Now we will talk about the history of the control systems. Control systems have a long history starting with ancient water clocks and evolving through. And we will divide the history of control system into four parts. The first part will be the early developments, and it contains the liquid level control like the water clocks, oil lamps, also temperature control like egg incubators, also the pressure control like steam engine safety valves, also the speed control, which is steam engine governors. The second part will be the 19th century, which started with the stability theory by Maxwell, Ruth, and Lyapunov, and that helped in ship steering and stabilization. Then we'll go through the 20th century. And the 20th century will contain the automatic shift steering (PID) control and feedback amplifier analysis by Bode and Nyquist and root locus method by Evans. And the fourth part will be the motor application, and that will be involve aerospace like spacecraft and aircraft, process control like the industry, everyday life like home appliances and entertainment. So we can know that the control system will be involved in our life. And here, as we can see in the figure, it's an optical playback system. As we can see, the objective links reading bits on the optical disc, and the optical path for playback showing tracking mirror rotated by a control system to keep the laser beam positioned on the bits. And now we will talk about the system configuration, and we will have two kinds of systems. The first one is open loop systems, and its structure contains the input transducer, which converts the input into a form usable by the controller. The second part will be the controller, drives the process or the plant. Thirdly, the process or the plant performs the desired function. As we can see in the figure, no feedback path. That means the output is not measured or used to influence the input. Again, and the characteristic of the open loop system is sensitive to disturbance. That means internal and external disturbance directly affected by the output without any correction. Secondly, limited accuracy. That means it cannot compensate for variation in the process or external factors. Thirdly, simple, which is generally easier to design and implement. And the example of the open loop system like the toaster rely on fixed time settings, ignoring factors like bread type and thickness. Also, the mass springs damper system with constant force. Position is determined by the force without considering the external forces. And we can see on the figure the structure of the open loop system. And the second type will be the closed loop system. The structure of the closed-loop system contains of the input transducer, which is also convert input into a form usable by the controller. Secondly, also the controller drives the process or the plant. Thirdly, the process or the plant perform the desired function. The fourth part will it's the difference between the open loop and the closed loop is the output transducer, which called the sensor. Measure the output, and it contains in the feedback path, which transmits the measured output back to the controller. And there is a junction in the structure called the summing junction, which compares the input signal with the feedback signal, so it can give the difference that from the input signal and compare it with the signal you got from the feedback or the sensor. And the characteristic of closed loop system, firstly, less sensitive to disturbance, which means can compensate for internal and external disturbance by adjusting the input. The secondly, higher accuracy, achieve desired output by continuously monitoring and correcting for errors. The third part, more complex and expensive, which requires additional components like sensor, which the feedback path, and more sophisticated control algorithms. For example, the thermostat measures the temperature and adjusts heating and cooling accordingly. Also, the cruise control monitors vehicle speed and adjusts throttle to maintain a set speed. Finally, we can summarize all this by knowing that open-loop systems are simpler but less accurate, while closed-loop systems are more complex but more accurate and robust. The choice between the two dependence on the specific application requirement considering factors such as accuracy, cost, and complexity. In this section, we'll talk about the key objectives of control system analysis and design. The first objective is the design transient response. That means achieving the appropriate speed and smoothness of the system's response to the input. For example, elevator speed, disk drive write and write and read, head movement. And the analysis involves evaluating the system's current transient behavior. And the design involves adjusting parameters or adding components to achieve the desired response. Secondly, we will talk about the reduced steady-state error. That meaning ensuring the system accurately maintains the desired output after transient effects subside. For example, the elevator levelness, antenna tracking accuracy. For analysis involves quantifying the steady-state error, and the design focuses on minimizing this error. The third objective will be the stability. That means ensuring the system's natural response remains bounded. That means decays to zero or isolates. But why stability? Because instability can lead to uncontrolled behavior, like runaway isolation. Stability is a fundamental prerequisite for achieving desired transient and steady-state performance. And there are other important considerations. For example, the hardware selection. That means choosing appropriate components like motor sensor based on power, accuracy, and other requirements. Also the cost, balancing the performance with the economic constraints. The other important consideration is the robustness. That means designing the systems that are not overly sensitive to changes in system parameters. In this section, I will talk about the design process, which is the steps for the closed loop or the feedback control system. The first step will be transform requirements into a physical system. That means translate user needs like desired performance, size, weight into a physical system concept and define specific design specification, for example, transient response, steady state accuracy. The second step will be draw a functional block diagram, like we saw in the closed loop and open loop system, how we can draw the functional block diagram, which represent the system using a block diagram showing the major components and their interconnections. This helps visualize the system's structure and identify key functions. The third step will be create a schematic diagram. That means translate the physical system into a schematic diagram including electrical, mechanical, and electromechanical components and make simplifying assumption about the system behavior. For example, neglecting friction, assuming ideal amplifiers. And uh, from the textbook, there is an example for schematic and antenna position control system. The fourth step will be develop a mathematical model using physical laws like Kirchhoff's and Newton laws and simplifying assumption to derive mathematical methods to find the models. And the common models including differential equations, relate input and output through system parameters, transfer function that provide a frequency domain representation of the system, and state space representation, which describe the system using a set of first-order differential equations to obtain the necessary parameters values for the model, for example, resistance and inductance and masses. The next step will be reduce the block diagram. That means simplify the system block diagram by combining blocks and reducing the number of signals. This results in a single block representing the overall system behavior. And the last step will be analyze and design. that means analyze the system's performance using test inputs, and evaluate transient response, steady error, and stability if necessary. Redesign the system by adjusting parameters, adding components, or modifying the control algorithm. And in this step, we will consider factors like sensitivity to parameters, variation, and environmental changes. And we saw this section provides a high-level overview of the control system design process, but subsequent chapter will delve deeper into each step, providing more detailed techniques and methodology to understand these steps. Now we will talk about the computer-aided design. Because the computers are essential for modern control systems, they facilitate faster analysis, simulation, and exploration of design options compared to manual methods. And we have two programs that can operate the control system very well. The first one will be the MATLAB. It's the primary software used in this textbook. It provides tools for analysis, design, and simulation, including the control system toolbox, Simulink, and other graphical interfaces. And the other one will be the LabVIEW. Is an alternative graphical program environment. It allows for intuitive design using virtual instruments. So by using these programs, the control system analysis will be easier and faster. Control system engineer. Control system engineering offers a unique and rewarding career path by fostering a multidisciplinary perspective. It encourages a top-down approach to design, connecting individual components to the overall system goals. This course provides a valuable framework for integrating knowledge from various engineering disciplines, such as electrical, mechanical, and computer engineering. By understanding control system principles, engineers can develop a common language and collaborate effectively across different fields. This interdisciplinary approach equips students with the skills and knowledge necessary to tackle complex engineering challenges and contribute to innovative solutions in a wide range of industries. So that's why the control system engineer is an important engineer in each field. And now, after we finish the chapter, we can summarize it as a key point. We can say that the control systems are ubiquitous. That means found in everyday appliances, transportation, industry, and even biological systems. The key components in the control system are input, process, and output. And the types are open loop, that means there's no feedback, and closed loop with feedback and error correction. And we can say in the design objectives that the desired transient response, that means the speed and smoothness, and reduce steady state error, that means the accuracy, and stability, that means ensuring the system doesn't become unstable. And we can understand the design process by understanding the steps of the design. The first step is determine the system and specification. Secondly, draw a functional block diagram. Third step will be create a schematic diagram. The fourth step is develop a mathematical model. And the fifth step is reduce the block diagram. And the last step will be analyze and design for desired performance. So that's all I have for the presentation of the first chapter of control systems. Thank you all for listening. والسلام عليكم ورحمة الله وبركاته.